You may have heard of digital twins, the metaverse and holography, but have you wondered what they are and how they relate? A digital twin is a virtual replica of a real-world object or system that can be created and analyzed in a similar manner to how it exists in reality. A digital twin could provide feedback as the product is refined, and it might even serve as a prototype before the physical counterpart is created. Digital twin technology collects data from IoT sensors, log files, and other relevant information to model assets accurately. These models are typically combined with AI-powered analytics tools to gain business insights into how a product or system already in use is working. On the other hand, the metaverse is a single, shared, immersive, persistent, 3D virtual space where humans will experience life in ways they would not even be able to in the real world, and serves as a digital twin of our physical universe. A hologram is a 3D image formed by interfering light or sound waves that reflect objects in the real world. Hologram technology has the potential to elevate digital twins to a new level by providing an immersive and interactive experience. In this episode, we will explore existing hologram technologies, their advantages and disadvantages in creating digital twins, compare them to digital twins in the metaverse, and discuss its applications. See how digital twins are revolutionizing industries from the military to healthcare as we step into the future, experiencing the power of hologram technology. Before we continue, make sure to subscribe for more on emerging trends in information and communications technology. Digital twins using holograms. It is possible to create digital twins using a variety of hologram technologies to simulate how its real-world counterpart will behave before it exists. Pepper's Ghost hologram technology is one of the most commonly used and the simplest amongst hologram technologies. A real or recorded image is reflected on a transparent screen, such as a projection pyramid, at a 45-degree angle. As a result, a reflected virtual image appears to viewers as though it has depth. Another hologram technology is laser holography. Holograms created using lasers are a more advanced form of hologram technology. In laser holograms, a laser, mirrors, lenses and a holographic plate is used to create a hologram. A hologram is created by reflecting a laser beam off a target object. The laser beam is split into two halves by shining it through a beam splitter. Another hologram technology is electro-holographic technology, also called holo-video, which was invented by MIT Media Lab. In electro-holography, computer-generated holograms are used to create three-dimensional images. Acoustic waves are used to modulate laser light. The method uses computation and optical modulation to produce large, interactive, color holographic images. The diffraction-specific algorithm quickly converts synthetic and real-world images into holographic fringe patterns. Displays utilize a scanned, time-multiplexed, acousto-optic modulator which diffracts light to form an image in real time. MIT researchers have also demonstrated a new method for generating holograms that can run on smartphones and laptops called tensor holography. It uses artificial intelligence to create holographic content in real time. With tensor holography, holograms can be created from images with depth information provided by a multi-camera setup or LiDAR sensor within a few seconds. Solid light holograms is another type of hologram that uses digital screens. Developed by Light Field Lab, solid light is the next generation of displays that combines ultra-high resolution and density to create objects that blend seamlessly with the real world. As part of its technology, solid light can recreate what optical physics refers to as a real image for off-screen projected objects by generating a vast number of viewing angles that accurately vary with the point of view and location, just like in real life. A direct emissive, modular, and flat panel display surface is used in conjunction with complex waveguides that modulate the dense field of collimated light rays. Each display is connected to a computer that contains several graphics processing units and field programmable gate arrays that provide processing power for rendering the images. Acoustic holography is another hologram technology. They differ from traditional holograms in that they use sound waves to create three-dimensional images instead of light waves. An array of speakers produces an acoustic wave that can be manipulated to create a particular image using acoustic holography. During the past decade, acoustic systems have gained greater capabilities, allowing them to levitate, push and pull small particles around using sonic tractor beams. Researchers at the University of Sussex in England have harnessed acoustic waves to create levitating three-dimensional images, create a sensation of touch, and even provide a soundtrack. An array of tiny speakers emits patterns of sound waves in the ultrasonic range, too high for the human ear to detect, which creates vibrations in the air that manipulate a plastic sphere the size of a sesame seed. Changing colors are projected onto the bead as it flies around in programmed patterns. As well as visuals, the system can also produce audible noise in order to provide a soundtrack for the display. Ultrasound speakers are also capable of concentrating vibrations in one place so that a finger might feel a sensation as if the object depicted by the floating image were actually in the area. The image can be viewed or perceived from any perspective or location within a room. One of the recent breakthroughs related to acoustic holography is in ultrasound imaging, which is used in medical imaging to penetrate human tissue. The use of 3D holographic ultrasound to manipulate and image human tissues could lead to the development of completely new therapies, including targeted neuromodulation. However, application of acoustic holograms in medicine are still limited because of their reflection and scattering by the organs and their internal attenuation. Since acoustic holography creates images using sound waves, it provides valuable information about the acoustic properties of objects and materials. Due to the capability of the technology to create three-dimensional sound images, viewers can experience a more realistic and immersive audio and video experience. Comparison of hologram technologies and digital twins. Compared to traditional digital twins, hologram technology facilitates a more engaging, immersive and interactive experience. By using holograms, user interaction with the digital twin in real time in a more intuitive and natural manner provides real-time feedback which enables a better understanding of the object or system being modeled. This can be particularly useful in research, systems design, training and education. The choice of hologram technology to be used in creating digital twins will vary depending on the specific application and cost. For small-scale applications, such as museum exhibits or trade shows, Pepper's Ghost technology is an excellent choice. Despite its relative affordability and ease of installation, it has limitations in terms of image quality and viewing angle. Laser and tensor holography is ideal for high-end applications, such as scientific research or art installations. Unlike Pepper's Ghost technology, it produces high-quality images with a wide viewing angle, but it is more expensive and complex. Electroholography, solid light and tensor holography are well suited for applications requiring high resolution, flexibility, and a wide viewing angle, such as advertising and product design. In spite of this, the process is still relatively expensive and requires specialized equipment and expertise. Acoustic holography may be preferred in applications that require the viewer to be able to view the image without a screen or special equipment, such as glasses or headsets. It is ideal for applications where the viewer may have to move and interact with the image, or perceive sound. Automotive and aerospace industries can also benefit from this technology, as acoustic imaging enables you to pinpoint the precise location of any noise-emitting sources, whether they are inside or outside of the vehicle or aircraft. It could be used in applications such as speaker design or other audio equipment. Consumer electronics can benefit from tensor, sound, light and acoustic holography, since immersive visualization and soundscapes can be created for movies, video games, and other forms of media. In engineering, acoustic holography can be used for the development of virtual prototypes for new products and for the evaluation of materials' acoustic properties. Ultimately, the choice of hologram technology for digital twins will be determined by the application's specific requirements, including the image quality, viewing angle, interaction, cost, and flexibility. Digital twins in the metaverse. Similar to hologram-based digital twins in the metaverse are virtual replicas of real-world objects and systems. In comparison with hologram-based digital twins in the metaverse may not offer the same level of immersion and interactivity. Virtual reality and augmented reality technologies are used to create digital twins in the metaverse, rather than holograms. Digital twins in the metaverse can be accessed using a wide range of devices, including smartphones and high-end virtual reality headsets, and by a broader range of users and applications. Applications of hologram-based digital twins. Holography-based digital twins are used in military systems to model, simulate, analyze and optimize the acoustics of complex systems, such as aircrafts, ships, submarines, rockets and other weapon systems. Military personnel can be trained by interacting more intuitively and naturally with digital twins using hologram technology, hence improving understanding, analysis and design of the considered systems. Healthcare is another application area of hologram-based digital twins. Researchers and doctors can analyze and simulate treatments more accurately and realistically by creating digital twins of patients, organs or specific medical conditions. Thus, patients may benefit from more effective treatments and better outcomes. In engineering, it can be used to develop virtual prototypes for new products and to test the properties of materials. Movies, video games, and other media can be enhanced with immersive soundscapes created with this technology. In the automation industry, digital twins can be used to improve manufacturing quality, reduce costs, increase flexibility, and reduce downtime. Emulated software replicas of wireless networks can be used for continuous prototyping and testing, as well as for examining congestion, security breaches, and equipment malfunctions. This enables the living network to self-optimize. It is believed that digital twins technology has the potential to transform and provide novel approaches to the construction industry. Digital twins may be used to redesign existing physical objects or to assess their performance. In addition to real-time monitoring, production planning and control, digital twins can also be used to predict maintenance, detect faults, and monitor the state of the equipment. In conclusion, hologram-based digital twins provide a more immersive and interactive experience than traditional digital twins. While hologram-based digital twins have some disadvantages, such as cost and limited hardware availability, they have large potential applications in a wide range of industries, including the military, healthcare, automation and construction industries, wireless networks, fashion design, 3D printing, interior design and more. We can expect to see more applications of holographic technology as hologram technology develops and becomes more accessible. Keep up with the latest breakthroughs in information and communications technology, subscribe today and stay ahead of the curve.